So thank you for the invitations. I'm Arnaud Jay. I'm a research engineer in energy efficiency in buildings at CA Liten. It's the French National Institute of Solar Energy. And I will present some prototypes we developed in order to give some advice to people when this is a good or not options to open the window regarding different criteria. As Hilda introduced, there's a lot of interest in opening the windows, especially that we can have natural ventilations for these open windows, which allow to exchange quite a lot of air change rate, much more than with mechanical ventilation system. So we can easily have 5 to 10 air change per hour for free. So it could be a really good options to bring for some fresh air in terms of indoor air quality or thermal comfort. But at some point, it can also bring some additional energy consumption or discomfort if it's done at an inappropriate time. So that's a bit of the scope of what we want to do. So we arrived to the coaching prototype, but how we arrived to this idea, we are working in an office building which is naturally ventilated, that you can see on these pictures. There is no air conditioning in this building, so in heat wave we are a bit hot, but we try to use in a quite efficient way the natural ventilation. So we have quite a lot of device for that. We can open safely the windows at night that you can see on the left pictures, and some windows to open the offices to the corridors without people can come in. So we put some sensors in order to see when people are using these openings. So this is so first that acquisition we have. And in parallel, we develop a tool to collect the feedback from users. How do they feel on their thermal comfort? So we monitor the building behaviors. So with the openings status, is it open or is it closed? So we use some contact sensors for that, for all the openings, from the office to the outdoors and from the office to the corridors. And then there is automatized opening strategy for the corridors to the exteriors, thanks to an atrium and louvers. We also are monitoring the fan use. So when it's too hot, we have some small fans in order to have some air velocity in our skins. So we have some parameters on that to follow this when it is on or off, and what is power needed. And we use some Z-Wave communication protocol with these different sensors, and this little plugin which are used to measure the power of the fans are also used to take the signal from the contact sensors to the Raspberry systems that collect the data. So we can have quite a lot of information for that. We can see how people are using the windows. How do they open the windows? So these graphs are for different offices. So each column is an office, and when it's red, it's not used, so it's closed. And when it's blue, it's like all time open. And on the y-axis, we have the hour of the day. So we collect all for each day the data at each hours, and we look at the percentage of the opening time. So if it's blue, it's open. It's red, it's closed all the time. So what we can see, it's like if we look at the louvers to the outdoors and to the corridors, that's most of the time people are using these systems at night time, and during the afternoon, most of the systems are closed. So this is some map for a summer period, in which, like in the afternoon, it's often hotter at the exterior side than in the interior. So it's better to close it. We also have some large windows that we can open when we are at the office, but not at night for safety reason. And for that, we see that there is quite a difference type of use of these windows, and the use of these windows are more in the morning. So when we come in the office, there is still some fresh air, so we try to open the more we can the windows to get the fresh air from the outside. We see that from some offices there is no strategy to open these windows. It is all right. And if we look at the fan, so the graph on the right part, we see that we are using the fan more in the afternoon and not at night when there is nobody. So this is the first feedback we can get from the user behavior, but just in an objective way. We also collect some data from how people are feeling. So we developed this small tool where we can collect the clothing strategy of people, how they are clothed, what are their clothes on the day they are filling the survey. Is there some potential annoyance in terms of sounds, visual aspect, olfactive that might affect their feeling? A little bit of redundant with the previous sensors, the office status. So the windows, the doors, and if we have some blinds for the solar gains. And then what is the most interesting is the thermal comfort with different questions regarding sensation, preference, satisfaction, and acceptance. A few questions about the air movement and global comfort questions. So we started this collecting this data from 2017 with, so it's now 7 years ago, we did this experiment during summer campaign. So almost 7 summers, but in some periods there was not such a big campaign, but we managed to collect 27,000 points from the feedback from users. And there is temperature sensors which are connected to the computer when we are at the office, who collect the air temperature in the office every 10-minute time steps. So we almost have 300,000 temperatures points. So when we look at that, so the right graph, we can see, okay, what is the user thermal comfort from different users, depending on their use about the opening of the windows or of the fans. So we put this, the pointer here, which are colored with the user thermal comfort, and depend on the running average of the outside temperature and the indoor temperature. And the dashed lines are the different limit of the user comfort, so the adapted comfort. So we can see that in some points, people are uncomfortable with quite red dots, but still there's not fan on, but still opening the window. So there's not very appropriate behavior. And in sometimes in this kind of case, it might be quite easy to understand that we are not acting in the best way for our comfort, but in some case, it's not so easy. So that was a bit the genesis of the Windows prototypes that we want to develop in order to coach people or to give some advice in order to know what is the best solution, taking into account 3 different parameters: the indoor air quality, the thermal comfort, and the energy consumption. And what is a bit tricky is that we can open the window. It would be a good solution to open the window for the indoor air quality, but not for the thermal comfort, or the opposite. So the algorithm we want to develop is try to see, okay, what is the weight we put in the indoor air quality or the thermal comfort? Or is it like one is very bad and the other is not so bad or not good? So the idea was to develop some sensors in order to collect the data from the indoor and the outdoor environment, and then to post-process this data in order to say, okay, it's a good option to open or to close the windows. So for that, we developed this prototype where there is 2 indoor sensors. So we are only measuring the indoor air temperature and the CO2 concentration, and 1 outdoor sensors with the outdoor air temperature that we need to put in the outdoor, but not in the direct solar radiation. So we need to take care about how we put the sensors. We take the opportunity to have an autonomous system. So we need to have like an energy and unbounded algorithm in this small prototype. And a key part was to give an intuitive message to communicate to the users because it's like not something with a big deal that need to be really annoy the people, but if they want the information, they should easily understand it. The algorithm we develop is based on 4 steps. So first, we will look at separately the criteria about the thermal criteria. If there are some potentials to open the window in order to refresh the air or heat the air inside the air when it is needed. And we couple that with the adaptive comfort models in order to say, okay, are we up to the upper limit or quite too close to the lower limit? So we need, okay, with this criteria, is it open? Is it appropriate to open the window or to close the window to prevent from overheating? And if we are quite have some exterior temperature close to the indoor temperature, plus or minus 1 or 2 degrees, we can say, okay, do whatever you want. There is no big deal about the thermal comfort. And then we look at the indoor air quality. For now, it's only the CO2 concentration. So if we go other threshold, we say, okay, it's better to open the windows. And if we are lower, to do whatever you want, there is no big deal about that. So we in the second steps, we check the consistency between the 2 separate solutions. So if it's like both are the same free modes, say, okay, at the end it's free. If one say open and the other say free mode, let's say open. And if both, it's one say close, a lot free modes close. And there is sometimes some conflict, which is like maybe the way we need to look at. And what we develop is an algorithm to say, okay, in which case I will say to open, in which case will close. So if the thermal comfort is quite high, we will say close if the CO2 is not too high, and get the CO2, the advantage if it's like a threshold is too high. So like that, we can push the advice to the user to say, okay, what is the best appropriate use of your window? So we developed this prototype and start to implement it in our offices last summer. So we had some first feedbacks. So you can see the prototype in here, in which people who are working in can easily see if it's flashing to say, okay, it's closed or open. And if it's like nothing is flashing, it's like the free mode. You can do whatever you want. You can always do whatever you want. It's just like an advice because we see that not all the windows are automatized. So if we could look at the first results, so we have like in orange part the indoor temperature, in black the external temperature with a different threshold about the adaptive thermal comfort in between the blue and the red line. So we have the thermal criteria, do we need to open or close on the yellow bar here. And we also have the CO2 concentration in purple with the threshold we define in this first version to 1000 ppm. So we have the indoor air quality criteria. And when we combine both, at the end, we say, okay, when it's only the thermal criteria set to close, to open, or to free, there is no conflict. So we can go with this advice. And at some point, there is some CO2 emissions which are higher than the threshold. So we can choose between both depending on the algorithm we develop. So that's so some first feedback. So summer is coming soon, so we'll have the chance to get some much more feedback and to adapt our algorithm to test it a bit more. And we have quite a lot of idea to improve this prototype in order to we need to get some feedback for in spring and autumn in mid seasons. The problematic about the battery autonomy is like for an autonomous systems, it's quite challenging to not have to change the battery or to plug in too often. We are also wondering if we need to implement other pollutant sensors. And opening windows is quite important in summertime, but yeah, closing the shutters in order to not have direct solar gain is like the first order and the first things to do. So we are thinking to integrate this, if we can integrate this kind of advice in parallel of the openings window strategies. So this is it for my presentation. So I will be pleased to answer your question at the end of this workshop. And yeah, now it's my pleasure to introduce Maxime and Mariva from the laboratory of University of La Réunion. And I will let them to introduce their speech.